Franck-Hertz Experiment. In 1914, at a conference of the German Physical Society, the two German physicists James Franck and Gustav Hertz presented the results of an experiment involving collisions between low-energy electrons and mercury atoms contained within a vacuum tube. The results demonstrated that for certain electron energies, the intensity of the electrical current dropped sharply.
Here, we have set up a modernized version of the experiment. Inside the heater, we've placed a vacuum tube containing a droplet of liquid mercury. The mercury atoms are still bound to each other, which is why the heater is required to liberate individual atoms. By selecting an adequate temperature, we can quickly obtain, by evaporation, a sufficient quantity of mercury gas required to study the collisions of electrons with mercury atoms.
A simple method of generating an electron beam is by utilizing a filament, which releases free electrons after being subjected to high temperatures supplied by an electric current. The free electrons are accelerated by a potential difference between the filament, acting as the negative electrode or cathode, and a positive electrode or anode. For example, if both electrodes are contained within a vacuum tube at a potential difference of 1 volt, the electrons will be accelerated to gain 1 electron volt of kinetic energy.
Using a mesh as anode, we determine the energies of electrons passing through it by placing a collecting plate or collector behind, so that between the anode and the plate, the electrons are subjected to a stopping potential of BF volts. Therefore, no electron passing the anode will arrive at the collector with an energy less than BF electron volts.
Franck and Hertz used a tube, much like this one, containing a metallic filament used for electron production. They also placed a mesh at a positive fixed voltage with respect to the filament. This way, the mesh attracted the electrons such that some of them passed through. Those passing through were accelerated by potential towards a second mesh, acting as the anode. Finally, electrons which passed the anode were slowed down by stopping potential until they reached the collector.
We have inserted the tube into the heater, which has now reached a temperature of 174 degrees Celsius. These potentiometers allow us to regulate the potential between both electrodes and the collector. The potential difference U1 between the filament and the first mesh and the potential difference U3 corresponding to the stopping potential BF previously mentioned will remain fixed, while we steadily increase the voltage U2 between the two grids until we reach a pre-established maximum. The variation with respect to time of the electric current IA registered on the collector, which by use of a suitable resistance is measured as voltage UA, can be observed on the screen.
To observe what is happening, we switch on U2, scale its values down by a factor of 10, and represent them graphically using a blue line, whilst the values of UA are plotted with the red line. On the x-axis, we have time. We notice that for certain values of U2, there are sudden drops of intensity. To better appreciate what is going on, we plot UA on the y-axis against U2 divided by 10 on the x-axis. The drops occur at intervals of 0.49 volts, implying that by smashing into the mercury atoms, the electrons have lost an energy equal to 4.9 electron volts.
Franck and Hertz noticed that this energy of 4.9 electron volts corresponded to a wavelength of 253.6 nanometers, which is a characteristic wavelength of Mercury's emission spectrum. In other words, 4.9 electron volts is equal to the product of the Planck constant h and the frequency nu. Since nu is equal to the velocity of light divided by the wavelength lambda, 4.9 electron volts is equal to h times c divided by lambda, implying a wavelength of 253.6 nanometers in the ultraviolet part of the electromagnetic spectrum. They hypothesized that the energy lost by the electrons might be emitted in the form of electromagnetic radiation by mercury.
To verify their hypothesis, another experiment was carried out. An ultraviolet spectrometer was used to analyze the light leaving the tube. It was observed that its wavelength matched the expected value and coincided with the drops in electrical current. Although Franck and Hertz thought that the value of 4.9 electron volts might be related to the ionization energy of mercury, that is, the minimum energy required to liberate an electron from a mercury atom, they concluded that another physical process might occur. Indeed, the data did not agree with what theoretical models at the time predicted for the ionization energy.
In 1915, the Danish physicist Niels Bohr estimated mercury's ionization energy using the atomic model he had proposed the previous year, according to which bound electrons can only exist in specific discrete energy states. As a result, he obtained a value considerably larger than 4.9 electron volts, suggesting that 4.9 electron volts corresponded to an intermediate transition between two discrete energy states. Bohr reasoned that the incident electrons collided with the atoms, exciting them. The following de-excitation of the atoms emitted the ultraviolet light which was observed. Later experiments showed that the ionization energy of mercury was 10.44 electron volts. This led Franck and Hertz to finally accept Bohr's proposal as a definite explanation of their results in 1918.
The regularity of the current drops is easily explained. The first drop of intensity, at 4.9 volts, corresponds to electrons which have excited mercury atoms in the vicinity of the anode and were then detained by the stopping potential. The second drop, at 9.8 volts, corresponds to electrons which first excited mercury atoms near the central part of the tube, then returned to excite more atoms in the vicinity of the anode, to finally be stopped by the stopping potential. In a similar manner, the subsequent drops are also explained.
We can only observe drops corresponding to the first atomic excitation. The reason is that other excitations occur at a much lower probability in comparison with the first, so they do not show up in experiments. One must also keep in mind that for voltages above 10.44 volts, ionization also occurs, but this does not affect the difference in voltage between the drops. Although the Bohr model does not correctly describe the structure of the atom that needs quantum mechanics, the hypothesis that the energies of bound electrons are quantized and that electron transitions between energy states imply the emission of light turned out to be perfectly valid, as corroborated by Franck and Hertz results. In summary, their experiment permits the observation of atomic transitions between discrete energy states using an ammeter and a voltmeter. This is an example of research in which the results transcend the expected ones by its authors.